For the very nice introduction. Hi, everyone. I'm Shi. I'm currently a assistant professor in the University of Waterloo in computer science. It's my great pleasure to be here to share some of my research work. I hope everyone can see my screen just to double check and can hear my voice very well.
Looks great and sounds great.
Yeah. Yeah, that's wonderful. As Grant has mentioned that my research focus are on building and design systems and tools for data analysis and machine learning that offer probable privacy guarantee and security guarantees. And today my topic is on the role of adaptive optimizer for honest private hyperparameter selection. So I hope through this talk, I can share some experience on how privacy changes the pipeline of machine learning when dealing with sensitive data, and how we can help non-privacy experts to choose optimal algorithms when they're dealing with sensitive data. Yeah, feel free to interrupt me if you have any questions. Okay. There's a lot of personal data has been collected in the past few years, and we know that they can be used for improving our services, such as product recommendation, or can use for scientific research, such as designing personalized or medicines, right? However, we also see that there's many news about privacy breaches take place in the past few years, and no mention about companies have to pay millions of dollars, right, for misuse of the data or sharing of the data without their users without the user's permission. And we may ask, how about machine learning applications that can deeply rely on personal data? Right, let's first take a look at our simplified machine learning pipeline. When we have some of sensitive data that can use for training, right? We train the model and release the model, or we can release the predictions that use the model over the live data. It seems that releasing such a model, which composed of millions of parameters, such as neural network, or just sharing the predictions should be fine, right? Because it doesn't reveal or give out the sensitive information of individual in the training data directly. It should be okay. However, a number of empirical studies in the past few years have shown that the model released can actually be vulnerable to several number of attacks, such as model inversion attacks, which makes use of the confidence score revealed together with the model prediction, right, can be used to infer sensitive information of the sample used in the training process. Or membership inference attack, right, which you can actually infer the use of a particular records in the training process as well. If we look at the pipeline a bit more, right, and in this pipeline, hyperparameter tuning is also very important step for us to ensure good quality model. And you can think about hyperparameter may just release a few parameters about the models, right? It shouldn't leak too much information about the sensitive data. However, one of the recent work also showed that, right, by just simply release or using the optimal hyperparameter choice over sensitive data, we can reveal information about the presence, absence of certain outliers. So we really have to be very careful to handle machine learning over sensitive data, right? One of the state-of-art privacy guarantee has been considered and ensure privacy for the machine learning pipeline, which is differential privacy. This was proposed in 2006 and have been applied in many of their data exploration tasks and also machine learning tasks. The idea of differential privacy is that the algorithm can ensure the distribution of their output is pretty similar for neighboring databases that differ in a single row. If we put into the context of training a model, right? If I train a model over database D and D prime that just differ in a single person's information or differing a person, so data has been used in the model or not, right? And the output of the model should have a distribution that's pretty similar, whether it's generated from D or generated from D prime. So when the adversary look at the output, right, And this adversary cannot tell whether it's generated from D or D prime, and hence to tell whether my record has been used in the training process or not. So in this privacy guarantee, there are two important privacy parameters here. First one is epsilon, which indicate the amount of information leaked through this training process, right? And the second parameter is delta, which indicate the failing probability to quantify the privacy loss by epsilon. Usually delta is said to be quite small. Okay, and there is a number of techniques has been proposed in the past to ensure a machine learning model is differential private. It could be noise injection in the input level. It could be noise perturbation of the output level. And one of the most popular techniques have been used in the past, including deep learning, is to design a differential private optimizer. Here I'm going to show one example known as differential private SGD or DPSGD. So the idea of DPSGD is actually quite similar as non-private version of SGD, right? First of all, you're going to initialize the parameter in the model and then take a sample from the training data and then compute the gradient over the sample, right? And then the difference between DPSGD with the non-private version is that here we have to clip the gradient to a bound, let's say C, and the idea for this clipping step is to ensure the contribution of one individual sample will not affect the output or the gradient in this case too much. It cannot be more than C, right? After the clipping of the gradient, we're going to add a noise to this gradient, right, to the clip gradient, so that we can hide, right, the contribution of each individual sample to the gradient. So to some extent, these provide privacy protection to whoever contribute or involved in this training process. And then we're going to descend the parameter of the model by using this noisy gradient or particular chosen learning rate. And this process will be repeated in similar fashion as non-private SGD, right? So this is pretty nice. And there's one way for us to quantify the overall privacy loss of this optimizer by considering a moment accountant method. Is one of state-of-art privacy composition techniques proposed together in the work for deep learning with differential privacy. So this idea is that you have T iterations of a noise addition process, and all the noise is drawn from Gaussian distribution, right? And the total privacy loss is actually proportional to the square root of the number of iterations you run this algorithm. So this is pretty nice and standard. And there are a number of more advanced, better DP optimizer has proposed in the last few years after DPSGD. And there are versions of non-adaptive optimizers and non-private setting be adopted to the private settings, such as DP momentum, right? There are also optimizers that have been popularly used in language processing, such as Adam, right? Those optimizers can also be similarly adapted to the private setting by using gradient clipping methods and noise perturbation methods. So, which is really nice. There are so many possible choices of DP optimizer that we can plug into our machine learning pipeline and make use of them, right? But as a non-privacy experts, right, when you look at so many optimizers, the kind of question we ask is, which DP optimizer should I use, right? Maybe we should just use the latest one that have been published in the recent conference, right? If we go and try it, and sometimes find out it doesn't work all the time for my data or for my application. So why is so? It has a similar reason as the ones in the non-private setting, right? The quality or the performance of the optimizer greatly depends on the choice of the hyperparameter. For a differentially private optimizer, if we don't tune the parameter that is hyperparameter to the best or to the close to the best, we can get a really poor utility as well. So the next question will be, so how should I tune my DP optimizer? Can I do it in a similar way as in the non-private setting, right? So I can try different configurations and then use the best configuration and train my DP optimizer with their given price budget, right? And the answer is no, this is kind of a dishonest behavior, right? And we have seen from our previous or earlier slides that if we use dishonest tuning, right, or directly use the best hyperparameter choice, we can learn or figure out the presence and absence of certain outliers. So what do we do? Is there something like public data set to support the tuning process? Right, the answer is usually we don't have such a nice public data sets for us to set the hyperparameter configuration, because the one that works the best for the public data sets may not necessarily work for my sensitive data. Right. So something nice about the literature in differential privacy is that there are also very nice algorithms be designed for differentially private tuning of optimizers. However, those work does not consider a particular differentially private optimizer. So these two problems, differential private tuning and differential optimizer, are usually studied separately, right? If we take the best algorithm for each of these components and put them together, they do not always guarantee the best utility, right? So that's something really interesting we figure out in our research work. And hence, our research goal is really to design and develop a usable system that can support machine learning process that achieve end-to-end privacy guarantee for non-privacy experts. So in this way, they don't have to know what exactly, or we can help them to choose the best algorithm, right, on their behalf, so that they don't have to look at the literature and try to figure out what works the best. In particular, the solutions work for each component or each step of their machine learning pipeline might not be the best choice for the entire pipeline. So in this, in the work that I'm going to talk about, the role of adaptive optimizers for honest private hyperparameter selection, we focus on this two-step differential private tuning and differential private optimizer, and try to find out what is our optimal solution or algorithm to support both at the same time. Okay, this is a joint work with my student Shubhanka and Sachin from University of Waterloo, my colleague Gautam and Om from Google. It's really nice to work with this group of researchers. Yeah. So first of all, let's take a look of the hyperparameter space for differentially private optimizers. We're going to look at DPSGD again. Right, compared to the non-private version of SGD, we have two additional parameters that we need to. That include clipping threshold, right? How much we should clip the gradients over the samples, and noisy multiplier. Then there are more differential private optimizers being designed, such as DP momentum, which add more hyperparameters in the space. And given this space of configuration for hyperparameter choice, right, how do we tune this DP optimizer? One of the first approach we consider is continue use moment accountant, right? So the idea is we have a tuning space of total K configurations. For each configuration, we're going to run or train the model once, and then find out the quality of this model, and then kind of report the best of the among the K configurations. However, we need to compose all the privacy costs among the K configurations. And for each of the configuration that take K iterations of noise, right, total together that K times T number of noisy gradients be learned or released. And hence the final privacy cost, if we're using moment accountant to compose the privacy loss of K configurations, will be proportional to the square root of K. So that kind of a straightforward way to compose the privacy loss when we tune the DP optimizer. On the other hand, there are more advanced techniques known as LT method proposed by Jin Chen and Kunal in 2019 in the work of private selection from private candidates. So the algorithm can be run as follows. For a sequence of K configurations, for each of the configuration you train the model, right? And then you flip a coin and decide whether you want to stop there or not, right? Once you decide to stop, you're going to output the best hyperparameter configuration that you have seen so far. So for this tuning method, right, their overall privacy cost, indicate here epsilon f, only depends on their epsilon 1 and delta 1, their privacy cost per algorithm or per model training. So which seems really nice because it doesn't really directly depends on the number of total number of configuration that you need to consider, right? So if we just look at these two expressions here for MA and LT, I probably will choose LT as my standard tuning method under differential privacy, right? So take this, to put this in mind, right? Let's try their best tuning method, which is LT, right? Together with the best DP optimizer. What is the best DP optimizer, right? Compare the non-adaptive one, adaptive one. When the previous literature have found out the non-adaptive DP optimizer that have been tuned well should work better than the adaptive ones. All right. So it seems a really nice idea that we have putting the best tuning method LT together with the best fine-tune optimizer, which is DPSGD or DP momentum. Right. So they should give us the best model. Unfortunately, the results doesn't work in that all the time. If we put these two together, we find that in our experiments that they don't always give the best results, right? Their fundamental reasons can be summarized as follows. First of all, there is actually a privacy overhead or blowed up for their LT tuning method. On the other hand, their non-adaptive DP optimizers such as DPSG have a large tuning space, right? So we're going to dive into these two factors one by one. Let's first look at the privacy overhead of LT. So here is the privacy cost for LT tuning method. Though we see that the final privacy cost epsilon f only depends on epsilon 1 and delta 1, which is the privacy parameter for each individual model training, right? This cost was derived from composing the T iterations of noise for each of the model training process. And when delta 1 is small, epsilon 1 has to be blown up. And this epsilon 1 has to be set to be quite small compared to delta f, which is the final failing probability, because delta f equals the square root of 2 epsilon 1, right? So when delta 1 is very small because of constraining the final failing probability delta f, epsilon 1 has to be big. And this blows up the final epsilon f, right? So when we have a small number of candidates to tune, the privacy cost have to be, first of all, have an additional factor of 3 and also a large epsilon 1. So this overhead can be evaluated or visualized here. We're trying to plot the privacy overhead for LT and MA respectively. If we just have a single candidate in the pool, we just want to train one model, right? And you can see the final epsilon expression for LT can be 5 times larger than the MA method, right? Even when the price of the data size is small, like 5K. And if we make use of these privacy overhead of LT, right, and try to train more candidates under MA methods, how many candidates can we actually train? And here is the results. When the data size is 5K, we can actually train about 20 candidates for using MA tuning method. And when the data size increases more than 1 million, right, the number of candidates allowed to be trained using MA is going to be more, it's about 200, right? So if the number of candidates trained is going to be small, MA is probably more preferred. And this is true for a number of adaptive optimizers. So to understand this problem a bit more, we look at the representative adaptive optimizer and a representative non-adaptive optimizer in the private setting. So for differentially private SGD, which is a representative non-adaptive optimizer, it can have a larger tuning space than DPAdam. So here is a visualization about the tuning space and the behavior of the tuning space of DPSGD. We plot the log of the training loss, right, over 2 dimensions of the hyperparameter space, including learning rate and clipping threshold. And I find there is an interesting inverse correlations between these 2 hyperparameter dimension, right? The good performing candidates are lying along the diagonals of this plot, right? So you actually have to tune both of these hyperparameter in order to get the best candidate. On the other hand, for DPAdam, right, we can actually just fix we can just tune along the clipping threshold, and then the learning rate can be adaptively adjusted, right? And this is a very interesting behavior for DPAdam, which is an adaptive optimizer. So when we just simply set or tune over the clipping threshold, we can get the best candidate without tuning their learning rate for DPAdam. So now let's try to put these 2 solutions, or the solutions from these 2 spaces together, right? In particular, if I paired up DPAdam with moment accountant, both of them are suboptimal solution for each of the independent problem for DP tuning and DP optimizer, right? They can actually incur much smaller cost than DPSGD or DP momentum paired up with LT tuning method, right? In order to achieve the same accuracy level. And we also experiment these results a number of data sets and a machine learning model. In these plots, we demonstrate the accuracy of the model trained on MNIST data sets and logic regression. So first of all, we're going to focus on differentially DPSGD and DPAdam and DP momentum. If we allow them to train over or tune them over the full space of hyperparameter choices. In particular, DP momentum will have 280 number hyperparameters, and DPSGD have 40 of them, and DPAdam has 4 candidates. And we can see that DPAdam, which is the green line, obtain almost a good accuracy as their other 2 DP optimizers. However, to achieve the same accuracy, right, the DPSGD method and DP momentum make use of much larger space of hyperparameters, and hence they consume more privacy budget, as we have shown in the previous slide. Right. So to achieve the same level of accuracy, the non-adaptive optimizer have to cost more privacy. On the other hand, we're to see if I really give a very tight privacy budget to the non-adaptive optimizers, whether they can get a good accuracy or not, and the answer is no. Right, so we randomly choose 4 candidates, but in some favor to the DPSGD and DP momentum methods. We can see the resultant accuracy of the model is not as good as DPAdam, given the same amount of privacy budget. Right, so the accuracy of these 2 methods under the same privacy budget is indicated by their dotted lines here. And the same results can be found when we are training a neural network as well. And we can see under the same price budget, DPSGD and DP momentum also have much worse accuracy compared to DPAdam. So it's really nice to consider DPAdam as an optimizer to be studied in the private setting. Right? We further investigate this line of adaptive optimizer and find something interesting about DPAdam. This observation is that the learning rate of DPAdam actually can converge to a static value at what we call the effective step size. So we can set up these effective size as the initial learning rate at the first iteration, and this helps us to save the second moment computation of DPAdam. Right, and here is the plot of the maximum accuracy and the median accuracy for 3 different differential private adaptive optimizers. And we can see the new adaptive optimizer DPAdam without second moment right, indicated by the red line, are doing as good as DPAdam, the original form of adaptive optimizer. And in some cases, the median accuracy can be better than its original form of DPAdam. So adaptive optimizer plays actually a very important role in the private setting, which shouldn't be overlooked, is claimed in the previous in the private work, right? So it is very important to look at multiple steps of machine learning pipelines all together. That's just a part of this picture, right? If we dishonest picking in one of the steps of machine learning pipelines, such as tuning process, we may result in more potential privacy attacks or suboptimal algorithm solution. And besides these two steps, there are many other steps in these machine learning pipelines, including model validation or data exploration, in order to decide more information about the training process. Even before obtaining or clean and good data sets for training, right, we have to collect the data from the raw, from initial sources, and process them all the way, right, until we get a good, clean training data. But this whole process requires looking of the data, the sensitive data, right? We should be really careful not dishonest picking the data, because that can leak or leads to a new privacy attack on these machine learning pipelines. So one of our recent work, a study about their data acquisition process, data cleaning process, and it showed that if we just picking the data without taking care of the privacy guarantee of those steps, it can result in a much larger privacy cost in the later steps. So this is something that we really want to get into and study on in terms of the entire ML pipeline, and how do we ensure full privacy guarantee for the entire pipeline. For each of the steps, we investigate and design solutions, such as how do we do differential private data cleaning and data exploration. And we also have work that deal with when the data has been distributed or further have it distributed over multiple sources, and how do we make use of crypto techniques to ensure that the data can be unionized and answered or be learned. And note that the raw source is not necessarily common with a single table, right? There are entities that are correlated with each other, and how do we come up with a more general privacy framework other than differential privacy or similar to differential privacy to quantify the privacy loss over them. So this is a very important problem for us to consider the machine learning pipeline as a whole rather than each single individual step, and to try to ensure their privacy guarantee. So yeah, for the time's sake here, come to the end of my talk. First of all, I want to really highlight that in this private privacy preserving tuning methods, right, it really depends on the optimizer as well, right? And it's not two independent problems, but we need to look at them together. And adaptive DP optimizer plays a very important role here. And every step of the machine learning pipeline is very important and require a careful treatment of the privacy concern if it touches the sensitive data. And the future direction will still focus on the tools that support each machine learning pipelines, and want to really build up end-to-end systems, ensure privacy guarantee for non-privacy experts. I'm happy to take any questions if you have. Thanks very much.
Thanks, Xi.